So we are in chemistry, chapter 15, and we're going to talk about pH. So what is pH? There's pH and there's pOH. First of all, they talk about the ionization of water. So the ionization of water, pure water, does ionize a little bit to a small extent when you have pure water. The Bronsted-Lowry acid test in the base is a proton transfer, not just the H and OH. But here we have, that's the way water, so like I said before, water can be, sometimes it can be acid and sometimes it can be base. So it does ionize to a very, very small amount. So here you have an equation of water. You have two water and water combining with each other, and in the midst they're going to make a little bit of acid there. That's the hydronium ion of acid. Here's hydroxide, the base. It's going to make a little bit. So even though you just have plain water, it does turn into a little bit. And what is the percentage of that though? It's not very much. It says in the protein transfer, equal numbers are produced. You have equal numbers produced in this. These numbers are very small amounts. And there are approximately one H3O and one OH in every 550 million molecules of water. Or the concentration is 1.00 times 10 to the negative 7th for each ion, each mole of each ion. So that's very, very small, 550 million molecules. Out of 550 million molecules, you're going to have one of these turning into a little bit of acid and a little bit of base. So that's the ionization of water. So let's go, and we're going to see how this links to pH in a bit. So because water and the hydronium acid and base are in equilibrium, then we can write this whole constant out, which we did before. And since the solutions of this acid and base producing are extremely dilute, the solvent of water is essentially a pure liquid. So when you have water, it's essentially pure, but 550 million, out of 550 million molecules, one will actually turn into an acid and base. And here is equation here. This is going to be called Kw, which is the equilibrium constant for this reaction. And so this is the constant. Here you have the H3O and the OH. This is the acid and this is the base molecule. And it's going to be called the ion product constant of water. So this is just showing this constant and what it is. And this number is going to be this, there's out of remember the 55 million or so, it says 1 times 10 to the negative 7th. There's going to be 1 times 10 to the negative 7th of the acid molecules, and there's going to be 1 times 10 to the negative 7th of the base molecules. And if you multiply those together, you get 1 times 10 to the negative, you add the 7s and you get the negative 14th. So in pure water, it's going to be 1 times 10 to the negative 14th. Now you're wondering, why in the world are we doing this? And you'll find out because we're going to put together a scale from this, and it's going to be a logarithm scale. Now, of course, in math, you haven't really learned logarithms yet. They're going to give you basically what logarithms are, but you have to have a scientific calculator and you can figure out these logarithms. So I'm not going to make you, I'm sure they're not going to make you calculate this out. It would be a big deal. But basically saying, water is going to be 1.00 times 10 to the 14th as you go here. And it also, this even varies with temperature. So you have to be at that temperature, 25 degrees centigrade, right? Approximately like room temperature there. So let's see why we're doing this. So because now we know the H3O and the OH are not always equal in a solution. So that would be a problem, but in neutral solutions, they are going to be considered equal. So if the solution has neutralized out, then the OH and the H3O will be considered. Neither one predominates and they'll be equal. So acidic would be the hydronium ion. If it dominates, then we'll be more acid. If the OH dominates, then it's greater than 1 times 10 to the negative 7th, then it would be basic. So when you take this solution here and there's more hydronium ions predominating, it's greater than 1.00 times 10 to the negative 7th, then you're going to have acid. If a solution has more of the other OH, then it's going to be a basic solution, depending on basic. So this is what we're really doing when we're talking about pH. pH is the acid scale that we're going to have. And there's going to be different ways of measuring this acid scale, but it's very important that we know, because pH, we use pH scale on everything to find out if something's acidic or not. In your blood, onto any type of solutions, water, anything. We can test anything and see, is it going to be neutral, is it going to be acid, or is it going to be basic? So that's how important it is. So the pH scale, let's talk about this pH scale here. The acidity or basicity of a solution depends upon the concentration of the hydronium and hydroxide ions, remember, in the solution. So, and this is the way we can test to see if it's neutral, if it's acidic, or it's basic. So here we have hydrogen and OH here, and we see they're equal. We measure it and they're equal. We're going to say, oh man, they're neutral, right? Then if we have a lot of hydrogen ions instead of hydroxide ions, you can see it's going to be acidic. Red meaning acidic. If it's basic, you're going to have a lot of blue, which is going to be hydroxide here. So this is how you measure. And you're really measuring what? To this scale. 1 times 10 to the negative 7th is going to be considered neutral. So if it's above that, if it's if hydrogen predominates above that, and if it's below that, that's how we get with the solutions here. So talking about the pH, we're going to go to the approximate pH here, but let's talk a little bit what this pH scale is. So just remember, pH scale is very important when you're talking about acid and bases. So we could sit down and we could write the number of H3O, which is the hydronium ions, the acid or the base here, hydroxide. We could just write these down, but instead, using that all scientific notation and everything, we found a scale that we can use. It's a lot easier. And the scale is a typical pH values that range from 0 to 14. So the lower the pH, the greater acid concentration, the greater concentration of H3O, which is the hydrogen, which is acid. The H3O is going to make it acid. Now, pure water and all neutral system, remember, water is going to be considered neutral at this, and they'll have a pH of 7. So the neutral number is going to be 7. Anything above 7 is going to be considered base, and anything below 7 is going to be considered acid. So when you have a low number, it's going to be very acidic. If you have a high number, it's going to be very basic, solution. So mathematically, the pH of a solution is defined as the negative logarithm of the hydronium ion molarity. So here it is. This is a little bit the logarithm deal that I talked to you about. So pH really is presenting the negative logarithm, which has to do over here when we're talking about H3O here. And so what is a logarithm? It says a common logarithm is simply another way to express a number as a power of 10. For example, 1,000 is going to be 10 to the third or 10 to the third power. And then on to the logarithm of 1,000 is 3. So you're going to take that third power and say the logarithm is going to be 3 then. Or the logarithm is going to equal 3. And similar, if you have a -2, the logarithm is going to be a -2. It has to do with that exponent. And they can be calculated with numbers that are not even integers. So then it goes on to this point. So to find the logarithm in that power. So that's what logarithms are about. Now that's just a basic way of describing it. Of course, you have a calculator to figure it out anyway, right? To find the pH of a given solution, simply find the logarithm of this hydrogen ion here, hydrogen oxide ion, which is hydronium, and that solution, and then change the sign. So for example, in a neutral solution, the logarithm would be 1 times 10 to the -7, 7. You change the sign, and the pH is going to be 7. In a logarithm, only the digits to the right of the decimal. Okay, but anyway, these are kind of hard to do if you don't understand logarithms yet, so I don't think you'll be dealt to do these. I did them. I put them together to try to put it, and I thought, I don't think you haven't learned about logarithms, so it's going to be a little bit hard to do, but you have to have a scientific calculator to do them. So let's go back up here. The approximate pH of some common materials. So you have 0.1 mole of hydrochloric acid. That is going to be really acid. 1 means it's very acid. Gastric juice in your stomach is going to be 1.7, very acid. Lemon juice, 2.3 acid. Vinegar, 2.9 acid. Soft drinks are acid, 3. Orange juice, 3.5 acid. Bananas are even acid, 4.6. Coffee is acid, 5.0. Rainwater is a little bit acid, 6.2. Blood now is neutral, 7.4. Egg whites are 7.8. So they're pretty neutral. They're kind of slimy. That means they're basic, right? Seawater is basic at 8.5. So, and then we have 1 mole of sodium hydroxide as 13. So you see here, the high is very basic, low is very acid. I'm not going to go over this whole logarithm because I don't think you're going to be able to really understand it right now. But here's how calculating pH is the negative logarithm of the hydronium atom there to find that. And going back to the monoprotic and everything. So this gets a little bit complicated. I'm not going to go over that. Now let's go on to the pOH scale, and that's going to be measuring not the H3O, the hydronium ion, which is the acid, but the OH, the hydroxide, which is base. It's just the opposite. So pOH is measuring the base. Using the pOH, the negative logarithm of the pOH instead of the H3O. So here we have the relationships between the pH. Acidic solution is going to be, the pH is going to be below 7, but in the pOH is going to be the opposite, above 7. The same, okay, here we have a basic solution. It's going to be above 7 for the pH. The pOH is going to be low. So pH and pOH are going to be exactly the opposite. You can tell why, because P is measuring hydrogen, and pH is measuring hydrogen, and pOH is measuring the hydroxide, which is base. So they're got to be opposite when you're talking about acids and bases. It says pH and pOH scales are closely related in any aqueous solution at 25 degrees. The sum of, you can take pH plus pOH, you're going to always get 14 if you add them together. So this relationship is convenient to find the pH. If you don't know the pOH and you know the pOH, you can find it by just subtracting 14 minus this to get the pH, or vice versa if you want to know the pH, because they're opposite. But if you add them together, you're going to get the neutral number of 14. pH measurement. Let's see. There, how do we measure them? How do we measure pH? What do we use? Got to have instruments, right? Well, of course, now we have a pH meter, an electronic one that does it. And it determines the pH of a solution by precisely measuring electric current generated when a pair of special electrodes are immersed in the solution. So here it is, a pH meter. And that's what I use. You put it in there, bingo, there's our pH number. That's very handy. But before that, and many other times, they use a less precise pH values, and they have other types of acid-base indicators, including organic acids and bases, and this has to also do with the color change. So litmus paper is one. And so when you have this organic dye that is blue in basic solutions and it's red in acid solutions, and we went over that and this will list how their color changes. And these indicators change color in their pH because their molecules tend to ionize at a particular pH, and at that losing it all at that time, and that going beyond neutral there, the indicator will be a different color. So here's colors of bromo cresyl purple, a different kind of indicator. And you see the pH 5 is going to be yellow, the pH 6 red, purple is 7. It changes color. So here's the phenolphthalein, and that too changes color. After pH of 8, pH of 9, it starts changing. pH of 10, it's purplish. Those are two different indicators. The main indicator that we're used to do is the litmus paper. Litmus paper is used all the time in laboratories, so we can just stick it in there and figure out because it's very quick at finding whether it's acid or base. So here we go, how the acid-base indicator here with 3-nitrophenol. And so you have the ionization. This is colorless. When it's in this position, it's going to look like colorless. Here's the hydrogen ion there. It's going to, and then you have water, of course, it's colorless. But as it changes here and forms the H3O with the water, the hydrogen comes off here. This hydrogen comes off and basically goes on, hooks on and makes it acid. Then this color changes to yellow because it lost this little guy. This little hydrogen atom went and combined with the water, making it an acid type, and then changing the color of the indicator here to a yellow. See, that's actually how it's put together there. So here's the equation. You have an indicator. It would be, of course, this would be the indicator, this molecule. It's a big molecule, be the indicator. So this is saying you have indicator, can be lots of different indicators, but you combine it with water, and then in the midst of this, you're going to see if it starts to, this molecule transfers over to make H3O instead of H2O, then the indicator will turn to a base color because it was an acid color, and now it's going to change to a base color as it. So basically, you know, this is called Le Chatelier's principle. Remember when we talked about Le Chatelier, basically saying it's shift. It's basically saying that the whole equation is shifting to one side, and that's what's happening here. It's shifting to one side as the acid molecule becomes apparent. The removal of these H3O ions from the solution tends to shift the equilibrium to the right, causing the color of the base to predominate. And then the concentration opposite you're going to see is going to shift to the left with the basic. So we'll see that the solution blue, when Bertholin blue is added, must have a pH greater than 7.6. So different indicators have different change at different pH levels. So let's look. It says other means used to obtain approximate pH values include universal indicator and pH paper. The universal indicator is a mixture of several different indicators, and it has a certain color. in solution on the whole range of pH. The thing is, you need to have one that has the right pH. If it's too high, then it's not going to detect some. If it's too low, it's not going to detect some too, on the other hand. So chemically treated pH paper turns a characteristic color as a specific pH value. And you could put it in as test strips. They use these test strips to find if something's acid all the time. So let's look at some of these indicators here. So if you looked here, this is the color. So this is the pH range that it's measuring. And if it's lower than this range, or at this range, color's going to be yellow. At the higher pH, it's going to turn blue. So the same, crystal red, all of these. Litmus paper is the common one we know. It's 4.5 to 8. That's the indicator. If it's below 4.5, it's going to be red, and that's pretty acidic. If it's above 8.3, which is pretty basic, it's going to be blue. This is another one, 8.3 to 10. So it's going to be basically above that range, which makes it at a higher pH, which is going to be mainly basic, but it's between 8.3 to 10. Each one of these, this is the indicator, and below this it's going to be this. Like here's one, below 10, it's going to be yellow, and above. This is measuring very basic things because they're on the higher dose. Because anything above 7 is going to be basic, and anything below here, the lower range, you're going to, so a very mid-range would be, of course, the litmus paper. Here's some pH papers mixed here to find out which pH they are and the colors that they become. These are all different kinds of indicators of pH. pH being whether it's acid or base. Okay, let's see here. Let's go through this a little bit here, these questions. How do the relative concentrations of H3O and OH compare in pure water? Remember, every 550 million molecules, or 1.00 times 10 to the 7 moles. So in water, it's very, it takes a very lot of them to make it acid or base, What is the pH scale? The pH scale measures the acidity or basicity, whether it's acid or base, right? And by measuring the H3O, and the OH in them. So it's that scale that they can measure that. At what pH is a substance considered neutral? 7, remember? 7. How are the pH and pOH scales related? You can add pH to pOH and you get 7. So how is pH estimated using the acid-base indicator? So an acid-base indicator, basically, how is it used? It suppresses the indicator at that point, Le Chatelier's principle, and makes the equation either go to the right or left. But in doing that, the color changes of the indicator. So, tell whether each of the following solutions is acidic, basic, or neutral. So should we look at these and see if we can just look and see? Well, we see right here. Let's look at the 10 to the negative 7th. You're going to know that it's going to be neutral because 7, that number is neutral. And here's 10 to the negative 2, 9.1 times 10 to the negative 2. I always think of, that negative 2, then it's going to be basic because you're talking about OH. You're not talking about, here you're talking about the H. So that it's going to be acidic. 10 to the negative 7 of H is going to be neutral because it's 10. But here you have OH. So now you say a negative 2 of OH will be the opposite, right? Would be the opposite because you're looking at the pOH or whatever. So a negative 2 would be a basic. And then here you have hydrogen. You have a negative 6 of it. you know that's going to be 9.1 times 10 to the negative 6 of the hydrogen. So you know that that's going to be acidic, because you're measuring the hydrogen here. Okay? So use table 15 to determine whether each of the following solutions is acidic, basic, or neutral. Well, when we look on there, we can look and see, you know, gastric juice, coffee, seawater. We went through the soft drinks. All of these are going to be acidic on that one. You can look at it. Gastric juice is very acid. Coffee is. Seawater is. Soft drink. Blood. Seawater is basic. I'm sorry. Gastric juice. Let's look at it real quick. I'll go back and look at it so I don't get things wrong. Here we go. Gastric juice on the pH scale is 1, acidic. Lemon, acidic. Vinegar, acidic. Soft drinks, acidic. Anything under 7. Orange juice, acidic. Bananas, acidic. Coffee, a little bit, almost neutral, but a little acidic. Rainwater, a little bit acidic. Blood is neutral. Egg whites, close to neutral here. Seawater is basic. So the one on there that I said, basically, seawater is basic. Determine the pH of each of the following solutions. I'm not going to do that. I did it, but it has to do with the logarithms and such. I'm not going to explain that whole thing. So tell what colors of the indicators litmus, methyl orange, and phenolphthalein would be in each of the following solutions. So let's go back to that here. Right here's the scale. So if we used, if we took coffee is at 5. So we took coffee at 5, and we're using, we're going to use a litmus paper at 5. So coffee is, what did I say it was? It's at 5. It's going to be what? It's going to be no change in color, because it's going to be neutral. So if we took seawater at 8.5, litmus 8.5 is going to be turn blue, because it's going to be it's going to be on the basic side, right? So orange juice is 3.5. Orange juice is going to be red, because it's going to be on this side of it, red. So because it's low, anything lower is going to be red, and that'd be acid. So blood is 7.4. So for litmus paper, right in the middle, it's going to be neutral. So because anything below and above. Lemon juice is 2.3, which is going to be totally acid. It's going to turn red here. But if you're using a different indicator, the other indicator, if you're using, let's see, the indicator of the yellow, let's see, the methyl orange here. So we do the same thing. So if it is, let's see, methyl orange. So if it is seawater, it's going to be 8. It's going to turn yellow orange. It's going to be basic. And so if it's, seawater, if it's orange juice, it's going to be, what's the orange juice is 3.5. It's going to be no change, because it's going to be right in the middle there, even though it's acid. So it's not the best indicator there. Okay, the same, we're not going to go over one, but they wanted you to use this one. So if we had coffee is 5, there's going to be colorless, because it's going to be no change yet. If it's a seawater, 8.5, 8.5 is going to be in the pH range. So really it's going to be, there's going to be no change. It's not going to be colorless, no change. So basically you won't get a change until it gets clear up into 8 to 10 range of basic before it changes. So this is not the best indicator in that way. So let's go back just to see how you do the pH. Is kind of fun. And so that's about it. I'm going to stop there.